Here we go. Small per out of the way. Okay.
All right, so this bunch of words means we need to find x such that x minus 2 is a multiple of 3, x minus 3 is a multiple of 5, and x minus 2 is a multiple of 7. And this is like the earliest problem, Chinese remainder problem that is also published by them. So how many of you know how to solve this? Okay, looks like a lot of you. All right, so
I think you need to click back onto the PowerPoint window.
oh, okay, thank you.
Oh, that's not bad.
I thought my clicker is not anymore. All right, so what kind of problem is this? So when people read, when you read that book by Sunzi, it doesn't say anything about what is used. It is like people that have written book in like the 60s that did historical analysis, and they were because of like what was important to people back then. That's when he said like, okay, it may be that it was used in troop counting or calendar making. So this is how it's going to look like if we are going to be using that to do troop counting. So you can say like, okay, order the soldiers into row of 3 and 2 men are going to be left over. Order them into row of 5 and 3 men are left over. Order them into row of 7, 2 men are left over. So that's kind of like an interpretation of that wordy problem before. So, and then we jump to 6th century. There is like the earliest also like written algorithm about how to solve the Chinese remainder problem, but only like with 2 modulus. So we have 2 equations, and you can see that the first algorithm is called Kutaka algorithm, and it is to solve this kind of Diophantine equation. And you can use it to solve the Chinese remainder theorem. So basically, when you have n as a rest of R1 modulo A and a remainder of R2 modulo B, this is equivalent to saying that AX minus BY is R1 minus R2. And this algorithm that I'm going to show you is equivalent to the extended Euclidean algorithm, but like what they're taking advantage of is the fact that when you have this equation right here, when you have ax plus by is equals to c, that's the same thing as GCD of a of these divided c. So what they are doing is like remove that factor, that GCD factor at each point. So that's the difference between the Kutaka algorithm and what we know now as extended Euclidean algorithm. And this is how it's explained. And again, I was planning on like going over it through you guys, but then it's a bunch of words, and I prefer to do the Euclidean algorithm with numbers and symbols. So I'm not gonna do that. So yeah, and when you see like why do those people have an algorithm for Chinese remainder theorem, that means that they have been using it, right? And the practical use that they are using it, again, they were using it for calendar purpose, because when you are doing calendar, you need to talk about like moon phase, the solar phase, and also the agriculture. So that's why you need those kind of modulus problem. And also they were using it for astronomy problems, so that like you do computation with planets and their period are different. But what I found like really cool is that they were also using it for religious purpose. I didn't know that happens. So they use altars of different shapes and size for different sacrificial goals. And when you build those kind of things, you need like different bricks. So some of the bricks that they were using are triangles, squares, rectangles, circle. So you need to do solve multiple linear congruences in order to find like how many types of the bricks are you going to use and how are you going to be arranging them. This is one of the altars that they have been using Chinese remainder theorem to build. Isn't it cool? All right, so now we do a big jump in time with Gus, which is I'm so grateful for him that he was introducing the term of congruences, because I may not even be interested in Chinese Remainder Theorem if it was written in Word instead of the congruence that we know now. So when in his book introduced Chinese Remainder Theorem with a problem to find the years that have a certain period number, and the things that he introduces, it was not like a new method per se, but what he introduces is like, this is how you write Chinese Remainder Theorem in terms of congruence, and now we have like this really, really nice form of solving it. So let's go back to define what the Chinese Remainder Theorem is, if you might have forgotten some of it. So we have numbers which are pairwise co-prime, those are the modulus. And we have given this kind of equation. So we have value x unknown is equals to a1 modulo m1, we have a2 modulo m2, and so on and so forth. And the Chinese Remainder Theorem tells us that you can go back x by doing this computation. So first, you are going to be taking like for each modulus, you are going to be computing this by, which is like the product of everything but that modulus, and then you are going to be taking the inverse of that product, and then you can have this very nice sum right here. That's your unique solution, and then it becomes like very mechanical. You just can do it by hand and solve it using extended Euclidean division. And that complete solution that we have now, it was published in 1247 in the mathematical treatise in 9 sections. And again, the use that they are using it so far is calendar making, astronomical calculations, and land surveying. And those are not something like we take the Chinese Remainder Theorem and we apply it to something else. It is like, okay, this is this problem, and we can write it as a Chinese Remainder Theorem. So to solve that problem, again, as I said before, now it's instead of like writing those paragraphs and letters, we can write it nicely. So here I can solve the problem in just one slide, because I can just tell it, okay, this is my I, this is my AI, I have 2, and then my MI, this is when the modulus is 2, we have when the modulus is 3, I have 5 times 7, that is my BI, and then I have like 35 is the same as 2 modulo 3, so its inverse is 2, because 2 times 2 is 4, and that's how we compute those 3 rows. And once we complete those 3 rows, we have the value of x. We know that it's going to be congruent to 23 mod 105. So now that we know what the Chinese Remainder Theorem is, how it was used in the old days, I am going to be showing you how is it used nowadays. And surprise, surprise, of course, I tricked you to listen to a talk about cryptography again. All right, so before I tell you about that, the Chinese Remainder Theorem doesn't like only work with number, it also works with any Euclidean division, which means like any Euclidean domain, which is a domain where the Euclidean algorithm works. So the statement of the theorem is exactly the same, except to have an Euclidean domain. The way that we compute it is still the same. And the way that we do everything is still the same. We just are using Euclidean domain. And you may wondering, like, why do we do that? Aren't numbers already hard enough? So these are the modern day use of Chinese Remainder Theorem. So things that I'm already implemented right now, and I am gonna go in more detail. First of all, is in the construction and speed up of the RSA algorithm. That RSA algorithm is what is securing your internet connection right now, your banking account right now. So we are going to see how cool is Chinese Remainder Theorem and how does help implementation of RSA. And the second is the construction and speed up for ML-DSA and ML-Chem. So those things are algorithm that was published in 2017, and they have been standardized in 2024 for NIST on their effort to having standardization of post-quantum algorithms. So it's really cool. So for the algorithm that we are using now and the algorithms that we are preparing to use in the future, Chinese Remainder Theorem plays a very big role. And those are some of the research. I just see that those are published paper, but I didn't see any implementation of those yet. But Chinese Remainder Theorem can be used to do secret image sharing scheme. And you can also use it to do image compression. And when you see something that says like number theory, something, it's usually have some Chinese Remainder Theorem in it. So and the last one here is you can also use Chinese Remainder Theorem to do like secret sharing. Basically, if you have like a number, then you just can like split the modulus and just give each of your parties one of those equation, and then they need to be together for them to reconstruct the original value. So let's go deep into RSA and ML-DSA. So for a very long time, people only been using symmetric key encryption. So how that works is, if you and I want to communicate, we need to meet in private first, and we exchange secrets called keys. And we talk about what algorithm are we going to be using. So if I want to send you a message, I am going to be using that secret key that we have with my encryption algorithm. And then what's going to comes out of that is like a gibberish that nobody will be able to read. And then since you have the same secret as me, you can plug that and the ciphertext that you receive from me, and you are going to get back the plain text. So what's wrong with that? First of all, we need to meet in person because before we can even talk. And second of all, if I communicate to 30 people, there are 30 keys that I need to keep track of, and nobody want to do that. So after like a lot of time, we have asymmetric key encryptions, and the first one of those is Diffie-Hellman 1976, the RSA in 1977, and how they work is, instead of me and you meet, I have like a pair of key. One of them is my public key, which I'm going to be posted, let's say, on the internet, and I have my the corresponding private key. So if you want to send me a message, you use my public key and encrypt it, and I am the only one who know my private key, so I am the only one who can decrypt it. So how that can be used? So again, this asymmetric key encryption, the way that it works is we need to use like hard mathematical problem, and when you have like hard mathematical problem that are like one way, that means that you need to do like a lot of math. So what people are using it right now is that they use asymmetric key encryption in order to share the secret key that you are going to be using for like the easy to do symmetric encryption. But even though you already like only sharing the key using the public key encryption, we still have like, since it's a large math problem, we may still end up with doing like a very big computation. And the type of devices that we are using are maybe might have like limited capacity. We want to use those on something like, say, your ATM, your like the door, something like that, which doesn't have enough memory. So we want to do like as much, make those as efficient as we can. And then now that everybody can send a separate message to everybody, also there is a problem. So the problem is, if you receive a message that says it's from me, how do you know that it's me that sent you that message? Because everybody now knows your public key. So digital signature is solving that. So let's say I want to send you a message. What I'm going to be doing is I am going to be using my secret key, and I'm going to be signing the message using my secret key, and then I'm going to be encrypting my message with my signature with your public key. I'm sending it to you. You are going to be using your own secret key to decrypt it. And now you have my original message and my original signature, and you're going to be looking up my public key, and you will be able to verify that it's actually me who sent it. And again, if you look here, we see RSA again. So there is like two versions of RSA. One is the encryption scheme, and one is the signature scheme, and they're kind of like the reverse of each other. And again, this El-Gamal, it's very similar idea to the Fielman that I talked to you on the encryption scheme. And again, here, the crystals, this is like the ML-DSA that I was talking to you about before. This is also like a friend that is an encryption scheme called ML-Chem, but today I'm going to be only talking to you about the encryption version of RSA and the lithium signature, but it happens the same way in the other version, so I don't want to do that into different text for the same idea. So, in case you haven't heard about it yet, RSA is based on the fact that when you have two large primes, it's very easy to multiply them. But when you have that product without any other knowledge, it's very difficult to factor it. So how can that help you doing encryption? So first of all, you select those large prime, P and Q, and then you calculate N, their product. And then you are going to be calculate phi of N, which you can do because you have P and Q. This is P minus 1 times Q minus 1. And then you take this integer E, which is coprime with phi of N, and it needs to be between 1 and phi of N. So it's E is small. And then you compute D, which is the inverse of E modulo phi of N. So when you have something that is small and is not 1, and you take its inverse, of course it's going to be big. So when you do the public key that you're going to be giving is E and N, and your private key is going to be D and N. So to do the encryption, the person who is going to be sending the message need to do C is equals to N to the power of E modulo N, and that is very easy because, as I said before, E is very small. It's between 1 and phi of N. However, the decryption, on doing that, you need to do the C right here to the power of D, because you know that E times D is 1 modulo phi of N, and then that's when you get N back. This is very large, because N is at least 2048 bits. So that's why we are going to be using the Chinese Remainder Theorem to make it easier to manage. So where does Chinese Remainder Theorem work in this? So again, we want to compute this more efficiently. And so since we only have like two primes, we have P and Q, we can do extended Euclidean division to write 1 is equals to P times Q plus QV, but then we don't need all of those two variables. We can write U in terms of V, so we only have like one variable. So now we take that when we have like a message, we take it modulo P and take it modulo Q, then you can write it like this. So this is exactly what we have before on the Chinese Remainder Theorem. We have n1 times q times v plus n2 times p times u, but you can write u in function of v. So now this p and this p, they cancel out, and then you can write this as m1 qv plus m1 times 1 minus qv, and then you can like rearrange them just a little bit to have this. And you may be wondering like, but it's still difficult. I still need to do this c to the power of a big number. Why do I bother doing that? Now, instead of using this big D, we are also going to take its modulo, its remainder modulo p minus 1 and modulo q minus 1. Why can we do that? Because when we do c to the power of d, we can rewrite it as dp plus some multiple of p minus 1. This dp now is smaller because we are taking the remainder, and then because of Fermat's-Leibniz theorem, we know that this guy right here is going to be 1. So instead of doing that exponential with a very big number, we now use very small power, like smaller power. So similarly, we do the same for reasoning works for Q, and now this is, instead of doing that decryption algorithm that I showed you before, this is how we do it. So first of all, you need to pre-compute and store as part of the private key P and Q, the DP, the DQ, and V, which is Q minus 1 modulo Q. And instead of doing the C to the power of D modulo N, which is very big, which is very difficult, this is what we do. First, you take M1, which is C to the power of DP modulo P, easier. M2, which is C to the power of DQ modulo, that's modulo Q, that's modulo Q. I'm sorry about that. And then you need to do H, which is equals to this V right here, M1 minus M2 modulo P, and then at the end, you just do M is equals to M2 plus HQ. And the benefit of doing the Chinese Remainder Theorem, doing this way, that this is even more efficient than computing exponential by squaring. So that's the benefit that we get. So the next one, ML-DSA stands for Module Lattice Digital Signature Algorithm, and again, we are using really big primes. That's why we care about efficiency. So this is the prime that we use for ML-DSA. I don't even want to read it. So why do we do that? First of all, the name is because the security is based on lattice problem, and it's funny that we are using a lattice because we are not working on like a plane where you can see the lattices. We are working on polynomial, but it's like if you are looking at lattice modulo on R, it's just like a grid of it's like grid, but just like try to imagine a grid made of polynomials instead of points. So the security of ML-DSA is based on the MLW problem, which means model learning with error problem, and it's very, you don't need to imagine that lattice with polynomials to understand it. Basically, if you are given a matrix like this, a matrix which is in that polynomial ring, and like row k columns, and then you are given this B is equals to AS plus E, S and E are small, or you can like given its distribution, then it is very difficult to recover S. So the most efficient algorithm known to solve this problem is the BKZ algorithm. It is not like specific for MLWE. It is used to find very short non-zero vectors in Euclidean lattices. So what happened when we know that that's the most efficient way. That means that when you know those, you choose a security level, then you can like work your way back to know what kind of Q, what kind of N, what kind of K, what kind of M you can use to have like that security level that you are targeting. So we have a range. So now you may be wondering, okay, so if I have a range, how do I know what exactly is the type of primes that I'm going to be choosing? And let me show you how the ML-DSA work, and I'm going to be showing you why all of those parameters make sense. So this is how we use it. So first you generate this matrix right here, and here we have, again, we have t is equals to as plus as1 plus s2. So if you were given a and t, it is very difficult for you to get back s1 or s2. So then when you are going to be signing, first you start with nothing, and then you chose a random y, and then you split it, you write it in base 2, and then you split it in half. So one of them is just like, they say it's the high bits, and the smaller part is going to be the low bits, and then you take that high bits, and then you plug into a hash function, and then at this point, you should not be able to go back to W1 anymore. So then you're going to be using that and add it to this computation with the random value that you get before. But still, this has this information about S1. So if you are not careful, some people may still do some computation and can, with enough value, you can find S1. So because of that, we are doing something called the rejection sampling. So the rejection sampling is you solve it, you compute this, but then you check that you don't have like the value to be if the value is too large, then you are gonna be doing the loop again until we have like low enough size. And it was already been computed that the expected repetition is between 3 and 7. And when you look at this right here, the things that we do like the most is again multiplication. So you have like AS1, you have AY, we have CS2, CS1. So if we can like reduce the multiplication of polynomials, we can make it like as efficient as possible. So in general, when we have like polynomial that we multiply, what we do is we do the school book multiplication, just multiply one polynomial times the other polynomial, and then we take it modulo q. And the cost of that is O of n squared. And when you are like using like the big prime as I showed you before at that range, anything like n squared is it's really expensive. And you can do like for any value of q, you can use like a more efficient multiplication, which is called and example of those are Karlsruhe and Hancock multiplication. And instead of having this O of n squared, you have O of n to the power of 1.5. And at the large scale, it's already like really good. And this is like work for any kind of Q. However, we can do better. We can do O of n log n thanks to, again, the Chinese Remainder Theorem. But it doesn't work with any types of Q. It needs like a special case of Q, and that's what the ML-DSA or ML-Chem is using to choose those value. It is those parameters are chosen so that the this trick is going to be work in speeding up the multiplication. So again, this is the Chinese Remainder Theorem again, but written in the concept in the context of ML-DSA. So we are going to have this value xt plus that this d, which is the power of 2. You're going to see why it is a power of 2, and you have this polynomial xd plus alpha, and if you can split it in product of two polynomial, again, the Chinese Remainder Theorem tells us that we can write this as, instead of like doing that multiplication on the big module, we can use it on the smaller module. And here the d's now half. So you may be thinking like, okay, but it's still of the half square then. But what happens is, if when you go like down, if you can like do dividing by half, taking the half at each step at the end, if you are lucky and ending up with like just a bunch of linear polynomials, then you will just like have one multiplication over CQ. Or even if you are not at that like lower level, if you cannot do that, if you can stop at like x to the power of 2 or x to the power of 3, you can still get an efficient multiplication rather than using that really big module that you are using. And the very important part is, if you, as before, pre-compute some of the values, then it's easy to compute the phi and the value of the multiplication. So this is how it works. So first we started this module right here. And instead of, you want to multiply polynomials a and b, you want to have ab. What you do is you go splitting, you do Chinese Remainder Theorem until it's split, totally split here. If you totally split here, this is going to be, instead of like doing computation modulo polynomials, it is just evaluating the polynomial, which is very easy. So instead of doing that, instead of doing this computation, you just evaluate the polynomial at this bottom line right here, and you work your way up. So that's, you reconstruct the product from this side right here, and the depth of this is log 2 of n. And at each step, you have the additions and n over 2 multiplications. So in total, instead of having that O of n squared, you ended up with O of n log n, which is huge when we are using that very high value of q. So again, this is what we need if we want that x to the power of n plus 1 to fully split. You will need q to be congruent to 1 modulo 2k. And why is that? Because that just means that 2k is going to be a multiple of q minus 1. So there is going to be an element of CQ star of order 2k. So that's why you chose those parameters. So that trick is called NTT, which is, say, number theory transform. As I said before, if you hear something that's like number theory something, that means that there are something that they are using Chinese Remainder Theorem inside of the algorithm. So this is a version of the fast Fourier transform that work over the finite field ZQ rather than C, and this is the n is equals to 256. We chose that because that is large enough, and that is the power of 2, and we wanted to split to the end. So the number theory transform requires ZQ to have an element R of order 2n, and that means in ML-DSA we always use this. This is already this is given in the specification of the algorithm. We just use it. Everybody just use this. And then since this polynomial fully split, then the entity is just a doing the entity transform is just evaluating the polynomial. So those are R0 minus 1 minus R0, those are the values that you obtain by doing that, by following the split of the polynomials that I talked to you before. I don't have like their value, but you know how do you get them. And now when you want to compute A and B, it's very nice because you're just going to be computing the entity of A times entity of B, and you are going to be going your way up using the inverse of the entity transform. So the benefit, as I said before, you have polynomial multiplication cost, but also it's a very nice, and I don't have like the time and space to explain it to you today, but you can read in the FIPS documentation about why when you are using this entity, you can also have like operations can be done in one place. So instead of like using multiple memory to do your multiplication, you can reuse your space, and that's very cool. So when you are looking at the ML-DSA, like the actual things that is being implemented, this is how it looks like. So first of all, that matrix A that you get, it is not generated as like matrix of polynomials. Instead, you are given the generated and stored directly in the entity form. And again, when you do those multiplication, those are computed as by computing the entity, and then you get back the entity inverse. And then every step that you have in the signing algorithm, you do that entity and entity inverse. It's a lot of them here. And again, when you do the verification, you will again use that entity to do every step of the verification. And if you are interested in any of the things that I'm talking to you about, on the things that I didn't have time to talk to you about, you can go and check the reference of the Wikipedia page. People say like, look at Wikipedia if you want to learn about scientific things. I've learned that you can still go to the Wikipedia, but just don't read the Wikipedia. Look at the bottom part where they have the references. You can see a lot of reference from there. And you can start from that. And this FIPS 186, this is where RSA is described. And so that's where you see that like how RSA is implemented and all of that. And this FIPS 204 and crystal stability on submission page, that is when you are going to be seeing what are the type of things that you do with ML-DSA. And that is what I have for you guys today. And if you have any interesting questions, you can ask it. I might be covering the Math Club talk next year.
Questions?
Yeah, do you know when people sort of call the theorem Chinese Remainder Theorem?
Actually, I didn't look at that.
Like, did girls started it or?
Oh, I don't know.
Yeah, that would be interesting. Like,
If you're teaching in South Carolina, just don't abbreviate it. Other questions? All right, let's think. I skip.
There's something